Good afternoon, everybody. This is Dawn Marshall at the University of Iowa. Welcome to the Safer Sim webinar series. Today we have presenters from the University of Massachusetts-Amherst on the topic of examining distracted drivers, underestimation of time, and overestimation of speed. Dr. Fitzpatrick, I'm turning the floor over to you.
All right, thank you, Don. So thank you for having me do this webinar. I'm excited to share the work that we've been doing at UMass over the past year or so. With me in the audience, I believe, is Dr. Nodler. He was the PI on both of these projects, so he can jump in with any questions or to answer any questions as well. So really, I'm going to be covering two safer sim topics that really dovetail into each other. The first on the topic of time pressures, and the second on the topic of time and speed perception. So the underlying research motivation for both of these was the topic of speeding. So speeding is really hazardous to driver safety. Nearly a third of all traffic fatalities are due to speeding related crashes. As speed increases, the risk of a serious injury for both pedestrians and vehicles increases. We really wanted to get to the root of why people speed and what we can do to prevent it. So NHTSA conducted a study or a survey a few years ago, and they basically asked, why do people speed? And the number one response was, I'm late. So, and another one was in a hurry. So that's kind of in line with I'm late. Here's my cursor. So in a hurry, 7%, and then I'm late, 35%. So this finding was really the underlying motivation for these two projects. So the outline for this short webinar, first I'm going to talk about the use of a driving simulator to determine how time pressures impact driver aggressiveness. So that is the title of the journal article that was published in Accident Analysis and Prevention just last year. So for this first project, when choosing participants, we wanted to select a population that was more likely to speed. So we pulled crash data from Massachusetts, and we looked at the proportion of crashes caused by speeding. So this is having a driver contributing code of exceeding the posted speed limit or driving too fast for conditions. And what we saw was a really clear trend for both males and females, where the proportion of speeding related crashes was highest at the youngest ages, and then we kind of saw an inflection point at around 30 years old. So with this underlying data, we decided to really use a younger, more student-based subject population. Among our participants, we split them into three different groups, a control group and then two experimental groups. And when I say groups, I don't mean three groups of drivers, but there were three groups of different drives. Oh, sorry. I'm mixing the projects up. So there were three groups of different drivers. So the control, experimental, and the second experimental. And really, the big difference between these two groups were the directions and the level of compensation. So with compensation for the control group, everyone got $30. And then with the experimental groups, we told them that their compensation would be variable based on their driver performance. So they'd get at least $15, but up to $30. And in order to get $30, they had to avoid crashes, avoid tickets, and then finish the drive under 16 minutes for the hurried group or 14 minutes for the very hurried group. So we wanted to see what effect of time pressures, so they're running late or they're trying to get somewhere in a hurry, what effect would that have on their driving performance? And these 14 and 16 minute thresholds were based on the 85th and 15th percentile travel times for the control group. So the hurried group was designed that only 15% of drivers would make it with normal driving, and the very hurried, or sorry, the 16-minute threshold was 85% of drivers would make it, and the 14-minute threshold was only 15% of drivers would make it. And then before we conducted the study, we gave everyone a aggressiveness questionnaire. And this was just asking them standard questions like, how often do you tailgate others to force them to move or deliberately prevent others from passing? And this really just allowed us to evaluate their underlying driver aggressiveness. And from this, we were able to basically state that the three groups were equal leading into the study. And then the really interesting part was throughout the drive, we gave them updates. So we didn't give them a clock or like a GPS that they could follow, but rather 3 times throughout the experimental drives, we gave them their drive progress and how much time had elapsed. So in this screenshot here, you can see that they've made it a quarter through the drive, and they've used a quarter of their elapsed time. So, and that's based on the 14 or 16 minutes. So this was given to them 3 times throughout the drive. So here's the full schematic of the virtual drive with all the elements that we were examining. So I'll go through it real quick. Hopefully you can see my cursor here. If not, they started down here at the bottom of the drive. They took a unprotected left turn with oncoming traffic. At these unprotected left turns, we were studying their gap acceptance. And then these blue squiggles are fixed speed collection points. There were 5 of them throughout the drive. Pretty equally spaced with the exception of the 3rd and 4th collection points, and I'll get to that in a minute. And then throughout the drive, we had these pass with care signs with passing zones. And there was limited oncoming traffic, or there was consistent oncoming traffic, and I'll get to that down the road. There were 4 red lights throughout the drive. After these red lights, we tracked their acceleration. And then these purple dashed lines indicate the 3 update points. So here they would see drive progress 25% with their elapsed time. And then they had another unprotected left turn. And then once after that second unprotected left turn, they came up to a straightaway where a slow moving truck pulled out in front of them. So here we wanted to test if they would pass by going into oncoming traffic. And then we went into kind of an urban zone with crosswalks. And then towards the end of the drive, we had 2 dilemma zones. So the green light turned to yellow at a point which was triggered by the driver's speed and position. So we wanted to see if they were willing to run the yellow light. So with that background, I'll go ahead and go through the results. So the first result was the speed. So as I mentioned, we collected their speed at 5 fixed positions throughout the drive. In the blue bars here, you see the control drives, the control group at the 5 points, and then the 2 red graphs are the experimental. So the black bars here represent a statistically significant difference between the checkpoints, and the white asterisks indicate a statistically significant difference from the control group. So for the control and the hurried groups, we really only saw a statistical difference between the 3rd and the 4th checkpoint. Now, going back a slide, the 3rd checkpoint was here in the urban setting with the crosswalks, so that's why we saw the lower speeds, as compared to the 4th checkpoint, which was without an urban setting. It was more of a rural setting. So we saw that statistical difference across all 3 groups. We saw the largest speed differences in the very hurried group. Now, in checkpoints 2, 3, 4, and 5, we saw a significantly higher speed than the control group, but we didn't see that significantly higher speed in the first checkpoint. And the reason for that is kind of interesting. So if we go back to our schematic here, our first checkpoint occurs before our first progress update. So the drivers did not know that they were running behind until they got this first update. So after they got their first update, then they significantly increased their speed as compared to the control. Now looking at the acceleration for the 4 red lights, here we have plotted the acceleration as measured by the speed at 7 different points after the red light. And then by taking the integral of the speed, or the derivative of the speed, we saw a statistically higher mean acceleration for the very hurried group as compared to the control group. But we didn't see a statistical difference between the hurried and the control group. And that will kind of be a theme throughout the results here. Now looking at the gap acceptance, so we had 2 unprotected left turns, one near the start of the drive and then one towards about the midpoint of the drive. And here we have the cumulative accepted rate, and then the dashed lines indicate the gap at which 50% of drivers accepted the gap and 50% rejected. So this could be the critical gap. Now for the hurried group, we had a critical gap of 4.8, or the very hurried group, we had a 4.8 second critical gap. And in the hurried group, so this is the less aggressive time limit, we had a 6 second. And if we look at this in terms of mean accepted gaps, we're able to statistically compare them. And again, the very hurried group had a statistically lower accepted gap than the control, but the hurried group did not have a significant difference. All right, so now looking at the willingness to pass the slow-moving truck. So looking up in the upper right-hand corner, we see the schematic about halfway through the drive. Just after the 50% update, a slow-moving truck pulled out in front of them, and the driver had to decide whether to pass them or just, wait for them to hopefully turn off. And in the control group, less than 10%, so I think that was maybe 1 out of every 12 drivers decided to pass the truck. And the percentages were much higher in the hurried and very hurried group. And again, the very hurried group had a statistically higher willingness to pass the slow-moving truck than the control group. And then looking again at the willingness to run the yellow light, so there were 2 dilemma zones at the end of the drive where drivers had to decide whether to run the yellow or not. And again, the very hurried group statistically ran the yellow light more often than the control group. And again, while the hurried group was higher, it was not statistically significant as compared to the control. So really we saw a trend throughout the drive that the very hurried group drove much more aggressively. The time pressure led to increased speed and acceleration, and the drivers were willing to accept smaller gaps. They were more willing to pass and run yellow lights. And what was interesting was that even though the hurried group had a time limit that was easily achievable, that really didn't require them to take aggressive maneuvers or to speed, just the very presence of a time limit or an incentive caused them, while not statistically significant, to basically drive more aggressively. So future work in this domain would look at different incentive structures in the driving simulator. So maybe incentivizing their drives differently based on using maybe a GPS, so constant tracking of their speed and position, rather than just 3 static updates throughout the drive. And then, of course, self-driving cars with the perception of time, or the time pressure component. So I think that's where some of the practical implications of this work comes in. So as autonomous features become more and more prevalent in vehicles, people are basically going to have to decide whether to let the car drive itself or to take control. So if someone is trying to get somewhere in a hurry and the autonomous vehicle is driving very passively and very safely, as I'm sure they'll be trained to do. Will the driver turn those features off and decide to drive manually instead? The optimal condition is for people to be in autonomous mode as often as possible to achieve the maximum safety benefits. So we'll just want to understand this phenomenon fully. All right, so this work really led us to the second project, which was thinking about time and speed perception. So in the first project, we were giving them speed updates and they had to reach a goal. In the second project, we wanted to see how drivers perceived their time and speed without really any cues. So this work was kind of spearheaded by a student, Andronikos, and then it's going to be published hopefully shortly in the Transportation Research Record. So in this project, we had 3 different drive types. We had an audio task, a visual task, and then a control group, or a control task. So in the audio task, the participants were asked to verbally respond to a sentence played through the speakers, and they had to identify the subject, object, and whether or not the sentence made sense. So an example would be, the ball bit the man. So in this example, the ball is the object, the man is the subject, and the sentence does not make sense. So the participants were asked constantly throughout the drive to respond to these questions. So it was basically like a cognitive load put upon them. And then in the visual distraction task, they were asked through speakers to locate a street on the map. So it'd be like, find Jackson Street. And then the drivers had a physical map that they had to find Jackson Street and relay the coordinates. And then in the control, there was no audio or visual distraction. And then all the participants drove one of the 2 experimental drives and the control drive. And the order in which they drove these was counterbalanced. And then at 5 fixed points throughout the drive, the participants were asked the speed at which they thought they were traveling and the time they thought had elapsed since the start of the drive. So we were measuring their speed and time perception. And throughout the entire drive, the speedometer was obscured and the clock in the car was obscured, and they weren't allowed to look at their cell phones or anything like that. So for the participants here we see the 4 combinations. So the control drive and the map, the control drive and the audio, and then the reverse order. In total, we had 34 participants, and you can see in the parentheses the number of participants who actually completed the drive. So we had a high number of crashing participants, and I'll get to why that happened a little later. And again, here we did the driver aggressiveness questionnaire to examine whether or not the groups were the same before the experiment. So going to the schematic, you'll notice this one looks very similar. So we used the same geometry, we just removed some of the components that we didn't really care about in this setting. So we kept the unprotected left turns. We didn't really study anything here, but just as a way to increase the stimulation of the drive. And then throughout the drive, we had 5 fixed points where this was where we asked the participants, how fast are you driving and how long have you been driving? So that's the exact language that we used. So getting to the results for this project, first with the speed perception. So this graph here shows the actual speed minus the perceived speed at each of the 5 checkpoints. So what we can quickly see is that at all the checkpoints in the 3 different groups, drivers perceived their speed to be lower than their actual speed. So in total, the mean was 5.6 miles per hour lower than their actual speeds. And the only significant differences was at the third checkpoint between the map task and the control/audio task. One possible explanation for this could be the map task was probably the most distracting because finding the streets on the map was very difficult, whereas the control had no distractions and the audio task wasn't too difficult. So it's possible they were able to perceive their speed better in these situations. Well, with respect to the time and time perception, so first, the actual time. So the travel time throughout the drive wasn't different between the control and the audio task, but the drivers with the map task took longer to reach the checkpoint. So really all this means is that the drivers with the map task drove slower than the drivers with the control and the audio task. And this is just more evidence that the visual distraction or the map task was more difficult than the audio or the control. Looking at time perception, overall, all of the participants in the three groups perceived the drives to take longer than they actually did. And this difference kind of compounded throughout the drive. So at the first checkpoint, they thought, maybe they'd been driving for 2 minutes when in actuality it was only 1.5 minutes. But by the time they reached the fifth checkpoint, their difference was around 3 minutes. So they thought they'd been driving maybe 16 minutes when they'd only been driving 13. And again, here we didn't really see any difference throughout the group. So the audio task had a little bit higher, not statistically significant. And the reasoning for this could be they were distracted but bored, whereas the map task, they were distracted, but they were very stimulated. So maybe it didn't seem like the experiment was taking as long. All right, so I discussed crashes at the very onset. I'm going to back up to the schematic here. So throughout the drive, we obscured the speedometer. We didn't have any speed limit signs, and we had these 90-degree curves with no curve warning. Well, we had curve warning signs, but we didn't have advisory speed signs. And that's because we really didn't want to influence or bias what the drivers would respond to with their perceived speed. And what that resulted in was kind of an unintended consequence of drivers approaching these horizontal curves too quickly, and then either running off the road or taking the curve too fast and then flipping the virtual vehicle. The way our simulator worked at the time was if you took a curve too fastly or too quickly, you could flip the vehicle. I think since the upgrade, the physics have changed a little bit that you can take curves slower, or you can take curves faster. But anyway, we had 6 drivers who crashed in the second drive, but not in the first. So what this meant was we could compare their time perception in the first drive to their second drive to see if we could predict anything. And we actually found a really interesting result here. So here our darker bar are the crashing drivers, and then our white bar is the non-crashing drivers. And what we're looking at is the perceived time versus the actual time, so their time perception. And this is in the first drive. And keep in mind they crashed in the second drive. So when looking at the crashing drivers in their first drive, they had this really big difference between their perceived time and actual time, and it grew throughout the checkpoints. So what this meant is they'd only been driving for 15 or so minutes, but it felt like 20. By comparison, the non-crashing drivers, they had a much better, actually a statistically better time perception. So towards the end of the drive, they'd only been driving 15 minutes, but they said it felt more like 17 or 18 minutes. So this kind of allowed us to draw the conclusion that the crashing drivers were kind of bored by the scenarios, and this caused them to increase their speed. So from their time perception in the first drive, we were able to predict their speed in the second drive. Um, that was just one finding from our 6 crashing drivers, and I think it'd be worth investigating further, either in a simulator study or a field study, but really investigating the link further between time perception and speed prediction. So getting into the conclusions of this second project, the participants overestimated their time and underestimated their speeds. And then a large number of participants crashed due to the lack of speedometer and lack of speed perception. So if I had to go back and do this study again, or if we were to follow up, I would do something different to the roadway geometry, or maybe provide a warning if they exceeded a certain speed, to try and reduce these number of crashes. So while the number of crashes kind of limited our sample size, it produced a really interesting result that time perception might be able to predict unsafe driving behaviors. So I went through those 2 projects kind of quickly, so I'd be happy to answer questions. I just wanted to give a quick plug for the Student Leadership Summit that UMass ITE is going to be hosting next month. So the Student Leadership Summit was, and I see Francis in the audience. I don't know if he has a microphone and wants to chime in, but it was basically an endeavor spearheaded a couple years ago out of California, and it's basically a way for students throughout a region to get together kind of for career and professional development. So we're really excited to host the first one in the Northeastern District, and we'd invite any SaferSim members or anyone on the call to consider attending. All right, so with that, I put my email in here and also Dr. Nodler's. So if anyone watching the call after the fact wants to send us an email with any questions, we'd be excited to chat with you. Otherwise, I'm happy to answer any questions from anyone who's here. So, and you're welcome to type questions if you don't want to use your microphone as well.
Hi, Cole. This is Dawn. I do have a question for you. What other people might be thinking. So the time perception in that second study, did you also measure simulator sickness or any kind of sickness scores? We
We
found that
didn't.
sometimes people drive
Oh, go ahead.
slower when they feel sick, or perceive the drives to be longer when they feel sick. So
Yeah, that's a great question. No, we didn't ask about simulator sickness throughout. We gave everyone a practice drive, and from my experience, I've been really kind of hyper that if someone is feeling just a little bit nauseous during the practice drive, I encourage them to not participate, just because you kind of get bad results if someone isn't feeling well. But it would be really interesting to link time perception and simulator sickness, because I have seen that same result, and I saw it in the first study with the time pressures. There were some drivers in the very hurried group who were like, I'm not going to make it. I'm not going to make myself sick trying to make it. So yeah, that's a good question.
for that after the practice drive, it sounded like, so that probably wasn't affecting your main drive. That was my question.
Yeah, thanks.
So I'll have another question about the first study. So you talked about setting the hurried and very hurried time goals based on percentiles of the control group completing the drive.
Yeah.
How did those times compare to how long it would have taken to complete the drive at the posted speed limit?
Yeah, so at the posted speed limit, that was basically um, the the hurried group. So basically, if you drove normally and not aggressively at all, you would make the 16-minute time. Um,
Okay.
so
And then my other that answers my question. And then my other question was, did did driving change after the time progress and time and progress notifications? And you answered that it did change after the first one.
yeah,
So
it definitely did.
so those were my questions. Based on those questions, is there anything else you'd like to point out or anything like
Yeah,
that?
so just going back to your last comment about the um, behavior changing. So when some people got to the 75% progress update in the very hurried group and they were, a couple minutes behind, they just kind of gave up on trying to reach the time the time threshold. And that would kind of be different than an actual time pressure. So in reality, when you're running late for something, it's usually not binary, I make it or not. It's how late are you? So I did notice kind of anecdotally that people gave up on trying to meet the goal when in actuality people would still drive aggressively to meet the goal. So had I not had kind of a binary success failure, I'd expect even more stark results.
That's a really interesting to me because what it tells me is that we need to tell them the drive is longer than the data we're actually going to look at, um, perhaps. Uh,
Yeah, like
you see what I'm saying? That the
yeah, no,
drive goes on for another minute, but if they give up, if some people give up in that, or enough people give up in that last minute, then it might be useful to collect an extra minute of data so that you don't get you might see that um, that last I can see in your results that things are it looks like the speed is going up that you might be able to see that go up in that segment.
yeah, or even maybe lie to them in at the final progress update and say like, you still have a chance of making it rather than you have no shot.
Yeah, those are both very interesting things because I wouldn't have thought that people would just give up. Um, you know, but I can see how they would do that.
Yeah.
You're right. When I'm in a hurry, I don't give up.
No,
I'm trying
right.
to get there,
It's
even
two
every
two
time.
minutes late isn't as bad as 5 minutes late, so you still kind of try and get somewhere.
Okay. Well, you've answered my questions, and it doesn't look like anyone's typing any questions. If you want to flip back to your contact information, so that's the last slide we have, unless there was another point you'd like to make.
No, I don't believe so. I saw Mike talking in chat, but not a question. So,
Yes, great job. Thank you very much for the very interesting presentation. I really enjoyed it. And if anyone watching the video or any of our attendees thinks of a question later, I'm sure they're welcome to contact you or Dr. Nudler with their questions at a later date. So I
yeah,
want to thank
please.
you very much and say goodbye for the day.
All right. Thank you very much, and thank you everyone for attending and listening.